it okay? All right. Yes, my apologies in advance to anybody who's watching this, because it's going to be like, very like, okay, just very, like if you've been on one of those like really cheap amusement park rides where you go on like a little train around something, whenever you go from like the straight to the curved, all of a sudden it's just like, ugh. We could like a lot of that. No one knows what I'm talking about. No, wooden roller coasters. We've all been on wooden roller coasters, right? Some of us against our will. Me personally. Oh yeah, this is an easy ride. This won't be bad. My brother and my now sister-in-law. Like, okay. It looks tall, and then I get on it, and it's just horrible. Just up and down, and so like, it's horrible, horrible. And it's like, and I lost my favorite hat. Oh, they say if you give you your address, they'll send it back to you. Liars. Liars. Dirty, rotten liars. Carowinds. Anyway. All right, I will begin with a word of prayer. So, it was 20 years ago. I should probably get over it, but anyway. Heavenly Father, we thank you for this day, for the snow stopping, so we can do some math, and I just pray you'd be glorified when we do this day, Lord. In your name I pray. Amen. All right, so the daily quizzes. Let us assess the damages. So here we have f of x equals xy plus 3. We have now this will not do. You're missing an f. With that, we're good. But the f is not optional. It's not that this is like an operator equals a function. That's just not going to work. Now this is good. Totally on board there. So what is a critical point? A critical point is one where the gradient of f is equal to 0, right? At a critical point. So I would like to see the equation. So we're looking for yx, and I think you're right. But it's just in terms of work, I'd like to see this written down. So that implies that y equals to 0 and x equals to 0 at the critical point, which of course then gives me that. So no, I mean, answer's right. The presentation here a little bit, well, it's not bad. It's not bad. Now here, we're on the right track. We're supposed to find the power series expansion of this function at 0, 0 to third order. So the point here is just to use the trick that we already know how to find power series of functions of one variable, right, from calculus 2. And so for something like this, we can just multiply those to find the multivariate power series, actually. So yeah, power series expansion of e to the y is this. But since we're going to third order, we're going to need one more thing. Right? Because that actually does meaningfully contribute here, because this times the 1 gives me a term that I need. Right? Now, what's this over here? This is the geometric series, right? 1 over 1 minus x is 1 plus x squared, and so forth and so on. So that's the geometric series. Great. And then so this is, let me just rewrite down here. What we're looking at here is f of xy, right? And so you got your 1 times 1 gives me 1. I'm going to write down here what I would do. So I get 1 plus x squared plus x cubed, right? That's what I get from multiplying 1. Multiplying y, I get y plus xy plus yx squared. That comes from multiplying the y, all right? Times all that. The 1/2 y squared gives me 1/2 y squared times 1 plus 1/2 y squared times x. That's what comes from this. And then this last one multiplies by that to give me a third order term, which I'll just write here, plus 1/6 y cubed. All right, so if I put it all together, I've got, let's put everything together here. I got 1 plus x plus y. Traditionally, we write things, the constant term, then linear terms, and then customarily, next we write the quadratic terms, which in this case are x squared plus xy plus 1/2 y squared. And then the horrible cubic terms, which I also asked for, I'll write them down here. I got x cubed. I've got myself a plus a yx squared. Do I have any other ones of those? I think this is the sole yx squared term. And I've also got a 1/2 xy squared. I think that's only one of those. Is there anything else cubic? Oh yeah, I've got the 1/6 y cubed. And there you go. that would be the power series to third order. So if I had any good sense, if I made this a test question, I would not ask for the third order power series. I would ask for the quadratic, because no part of me wants to grade this. Like making sure you get all 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 terms correctly, that seems like a drag. In contrast, if I just asked a quadratic order, I would be asking for this much, right? The quadratic order is just those terms. That I could grade without worrying that I was unjustly persecuting some of you for correct answers, you know? Any questions about this? The method is fairly simple. We just write down the power series expansions for the functions which are being used to construct the function of several variables. By the way, we can read things from this. So remember that there's a multivariate Taylor series, right? What does that look like? At 0, so here's what it looks like. F of x comma y, it's equal to, well, in the case, if we were expanding at 0, we have the first term is f of 0, 0. Then we have fx at 0, 0 times x plus fy at 0, 0 times y plus 1/2 fxx at 0 times x squared plus fxy at 0, 0 times xy plus 1/2 fyy at 0, I forgot my 0, 0, 0, 0, okay, 0, 0 y squared, and so forth, right? So if you compare the start of the Taylor expansion to that answer, you could tell me things like, for example, what's the value of the function at 0? It's 1. What's the first derivative at 0 in terms of x? It's 1. First derivative in y at 0? 1. What's the second derivative in x at 0? You say 2. Why do you say that? So you're like 1/2 fxx at 0, 0 is equal to 1, yeah. The coefficient is 1. So you're equating coefficients. So yeah, that would be 2. Now, of course, you could also just calculate those derivatives directly from the function in this case, right? But, I mean, it is kind of nice if you look at it. This would allow us to calculate 10 partial derivatives evaluated at 0, 0 if we just compare the coefficients with the power series expansion. All right, well, enough about that. Any questions? Okay, let me take these off. Ugh. Now this one here, so this time I actually gave you the power series expansion about what point? About the point 1 minus 2, right? And I said calculate the partial derivatives. So the point here is that what we should have in mind, right? I'll just put it up here, squeeze it in, is that f of xy is equal to f of 1 comma minus 2 plus f sub x at 1 comma minus 2 times x minus 1 plus f sub y at 1 comma minus 2 times y plus 2 plus 1/2 fxx at 1 comma minus 2 x minus 1 squared plus the xy derivative, mixed derivative, at 1 minus 2 times x minus 1 times y plus 2, and so forth. All right? So I can read from the expansion which is given some things, right? So you should just compare. So what is f of 1 minus 2? This matches that. So f of 1 minus 2 is 10. Which is not listed. Okay. Did you get fx right? Now you're actually differentiating. There's no need for that. It's just a question of interpretation. But you might have got the right answer, though. Maybe. Really, the only thing that should survive here is the 3, right? If you plug in this point into this expression, that drops out, and you're just left with 3. So this is that 3, okay? 3 is equal to the x derivative at that point. The y derivative is equal to 2. Fx, so I'm going to just, so there's no need for differentiation is my point, and sorry, it was a lot of writing, I know. And in right place, but sorry. But that is not how to do it. This is just a question of interpretation. We have to understand what the multivariate power series tells us about partial derivatives of the function at the point around which the power series is centered. Right? Just like Taylor's theorem, but for several variables. So this gives me 1/2 fxx of 1 minus 2 is equal to what's the coefficient in the given series? It's 6. All right? So therefore, fxx of 1 minus 2 is equal to 12. It's not wrong. I mean, what I just erased might have had that answer correctly. I don't remember. It did. See, so it's true. You can differentiate and do it, but that's just this completely unnecessary calculation and not the way we should do these. All right? Let's see here. On the other hand, what's fxy? And it's also fyy. These are both 0 because there is no such term in the expansion. Right? So it's understood in this kind of problem, if I stop with the quadratic, I will never give you a thing to work on where I've given you just half of a particular order. Like, it's understood, it's our custom that the expansion, if it's got plus ... it's all the way up to the given order. In this case, quadratic, yeah.
Where would those terms be if they were in that equation? Or like, what would the
Oh, sure. If there had been, well, they look like this at the moment, 0 times x minus 1, fair question, y plus 2, and then 0 over 2, y plus 2 quantity squared. All right, so next one up here. Problem 4. I gave you the power series expansion for a function of 3 variables centered at 0, 0, 0. And I asked you to determine whether 0, 0, 0 is a critical point, and if it is, to analyze the type, min or max. So again, the point here is one of interpretation. So, you know, it's f of x, y, z. It's equal to f of 0, 0, 0, right? Plus the gradient of f at 0, 0, 0, dot product with x, y, z. Plus, well, then we have 1/2 fxx. Oh, so much writing. 0, 0. I'm just going to write 0. Okay, at 0. That's the 0 vector. X squared plus 1/2 fyy at 0, y squared plus 1/2 fzz at 0, z squared plus fxy at 0, xy plus fxz at 0, xz plus fyz at 0, yz, and then higher order stuff. Actually, we don't need all that for this problem. We really don't. The point is, if the gradient is non-zero, what does it show up as? Yeah, it shows up as linear terms. So this here, if I write it out in more detail, is what? I mean, this is really my just shorthand for fx at 0 times x plus fy at 0 times y plus fz of 0 times z, right? That's that piece of the power series expansion. If that's not present, that means the gradient is 0, which means it's a critical point. So for problem 4, the answer is yes, it's a critical point, because when we look at this right here, right? Missing what? X, y, z terms, right? Just plain x, y, z terms. They're not there. That means the gradient of f. The gradient of f is equal to 0 at 0. Right, which is to say that it's a critical point. Now let me look at what's written. So again, you took more or less the approach that the person who was working problem 3 did, which was to differentiate it and set it equal to 0. And yes, it is, because if you set the derivatives equal to 0, We get that 0, 0, 0 solves fx being 0, fy being 0, and fz being 0. That was your logic, right? Yeah. Not wrong. It's just that that work is not necessary, right? Like, there's no need for differentiation. All you have to do is look at this and go, there is no x, y, or z term. So by the fact that we know the multivariate power series expansion, this is my theme, you need to get to know the multivariate power series expansion, at least a quadratic order, in 2 and 3 variables. If you know that much, you're pretty much good to go. Then we can read directly from this expression that there is that 0, 0, 0 is a critical point. Now, past that, Nathaniel was starting to suggest to you to look at the Hessian and so forth and so on, but actually this is just a common sense problem. So we're given an expression in terms of sums of squares. So just think about it. If we take, at the origin 10 and we go any which way, what happens to the value of the function? If you increase, if you let x, y, z go away from 0, 0, 0 to something, comma, something, comma, something, how does that compare to f of 0, 0, 0? What are you doing? You're adding sums of squares, right? So no matter which direction you go in, you're doing what? You're making the function larger. So f of 0, 0, 0 is a what? It's a relative it's a local minimum, right? So, I guess technically it's probably, I don't, without the plus dot dot dot, I can't say about global, but certainly f of 0, 0, 0 is equal to 10, and that's a local minimum for the function. I don't need a second derivative test, just common sense. And the fact that if you're close to the critical point, the lowest order terms in the power series expansion dominate. Think about that. If you're really, really close, if you're like within 0.1 distance from the critical point, this is size, how big is this? This is like 0.01 in terms of its magnitude. Like 0.1 times 0.1 squared is like 0.01, right? How about the cubic terms? That would be like 0.1 cubed. How big is that? It's 1/1000. Can't say words. 1/1000th. It's way, way smaller than the quadratic piece. So the lowest order piece, which is non-trivial, completely dominates the behavior of the function near the critical point. That's the point of looking at these power series expansions, is that it allows us to look at the function term by term locally. So, there's that. Now this one here, same instructions problem 4, f of 0, 0, 0 is 13. Check, didn't ask for it, but okay. Fx of 0, 0, 0 is 1, indeedly. Fz is 0, I agree. Fy is 1, I agree. Fxx is -2, -2, 0, -2. I agree with all these things, but I did not ask for them. What was the question? Is it a critical point? And if it is, analyze the type of critical point. So is it a critical point? What's the gradient of f at 0, 0, 0 in this one? So is it a critical point? No. 0, 0, 0, not a critical point. So you can't analyze what kind of critical point it is because it's not a critical point. All right? Yes? Uh-oh. Josh foresees. This is interesting. But no. Let's get on with it here. It's fine, Josh. I know you guys are all still, that might have been right what you just wrote down here, but anyway, the point is, you look at this. What's the gradient of f? There is no x, right? There's 0 times x plus 0 times y plus 0 times z here, if you look really careful. Can you see those? 0x plus 0y plus 0z. I mean, they're not there. So that means that the gradient of f is 0, 0, 0 at 0, 0, 0, which is to say that indeed the origin is a critical point for this function. What kind of max or min or neither is it? So this one here, f of 0, 0, 0 is equal to 13, right? That much is clear. But if you look at it, this is what, is this a minimum or is it a maximum? What can you tell me? Let me just guide your thinking for a second here. If we look at something like, say, f of x, comma, 0, comma, 0, what do we get? 13 plus x squared, right? Exhibit number 1. Exhibit number 2. If we look at f of 0, comma, y, comma, 0, what do we get? 13 minus y squared, right? So if I fix y and z to be 0, and I change the x, I do what? I increase the values of the function along that direction, right? But on the other hand, if I fix x and z, and I just change the y direction, I decrease the values of the function, right? So if you were to, it's like a parabola that opens up in the x direction, it's like a parabola that opens down in the y direction. This is what's called a saddle point, because it increases in one direction away from the critical point, but it decreases in the other direction at the critical point. So f of 0, 0, 0, so 0, 0, 0 is neither max nor min. It's a saddle. But here, this term saddle point is not meant in terms of, when we're looking at a function, our first problem 1 here. What kind of critical point is this? F of xy equal to, xy plus 3. What kind of critical point is that? And why can't I just, I just use common sense, right? Common sense to analyze whether the origin was a critical point for problem 4 or problem 6. Common sense won't do it here, xy. Right? Why is that? What's the difference between xy versus problem 4, 5, 6? In problems 4, 5, and 6, we don't have any cross terms. There's no mixed terms, right? It's just sums or differences of squares. If you just have sums or differences of squares, you don't need linear algebra or anything fancy to figure it out. You can just say, if they're all pluses at a critical point, it's a local minimum. If you're taking the value of the function minus a sum of squares, it's a local max. If you have pluses and minuses of squares, it's a saddle. That's it. Where it gets complicated is when there are cross terms. And only in 2 dimensions do we really have the technology in here to solve that. Because if you have a 3-dimensional function of 3 variables, well, then you need linear algebra to sort out what kind of cross term you're looking at. It's a question of linear algebra, unfortunately. But here we also have the what? The second derivative test, right? So let's see here. We've got f of xy equal to xy plus 3. We just figured out already that the gradient of f was yx. And we noticed that the gradient of f at 0, 0 was 0, 0. Right? So thus 0, 0 is critical point. So what's the nature? What's the nature of the critical point? Is it a min? Is it a max? Is it neither? Oh, is that right? But are they? Well, yes. Let's see here. fxx at 0, 0 is what? fxy at 0, 0 is what?
Wait. fxx oh, sorry. Okay.
I think I agree with you about the fxx and the fyy. Those are both 0.
Did I say fxy? I entered xx and y.
You said xx and yy, and you're right. Those second derivatives are both 0. But the mixed derivative is not 0.
That's 1.
Which, yeah, we could just, it's 1, yeah. So we calculate the Hessian, right? Which is usually called big D, which was what? It's fxx, fyy, minus fxy, right?
Squared. Right.
Oh, squared, yeah. Sorry. Here's my cheat. That's the determinant of this matrix. How's it go? Yeah, fxx, xy. The determinant of this little 2 by 2 matrix gives you that, you know? The determinant of that little 2 by 2 matrix is actually the product of its eigenvalues. If both of those eigenvalues are positive, it's a local min. If both of the eigenvalues are negative, it's a local max. If one eigenvalue is positive and one eigenvalue is negative, it's a saddle. Correspondingly, if d is less than 0, that would be the product of the eigenvalues being negative. That means it's neither a local max nor min. But if d is positive, you have to look at the sign of fxx. That's what we derived anyway. So let's work it out. What is d? I mean, I'm not going to go through it again. I spent the better part of the last, hour of lecture establishing this test. It was a pretty long proof, really, right? So what do we got here? 0, 0 minus 1 squared, right? So that's minus 1, which is less than 0. So thus, f of 0, 0 is at a saddle point. And here I actually mean it directly in terms of the geometry of the graph. If you were to plot z equals x, z equals xy plus 3, what would it look like? I know this much. This point's on the graph. I know more. I know if x and y are positive, we're doing what? If x and y are both positive, the product of x and y is positive, right? What if x and y are negative? It's positive, right? What if, so if you think about that, and you think about the 4 quadrants, right? xy is positive here, right? xy is positive back here. xy is negative in this part of the xy plane. xy is negative in that part of the xy plane, right? So that says that the graph grows up in that way, right? But it goes down in that way. So it's something like it drops down here, it drops down here, and it goes up here, and it goes up there. It's a saddle. You could put it into Wolfram Alpha or Mathematica or whatever floats your boat and see it if you like. So, all right, thinking about the, your index card for the next test. What's one of the things that ought to be on there? Yeah, obviously you want the second derivative test, right? Doesn't take up a lot of space, but you need to know it. When does the second derivative test apply?
When the determinant of the Hessian is non-zero, right?
When the determinant, well, oh yes, when the determinant of the Hessian is non-zero is true. Good point. Certainly we need to have some second derivatives, but, another thing I could say, we need some second derivatives to be non-negative, right? But before all that, when can you look at the determinant? When can you look at this d to decide whether a critical point is a maximum or a minimum or neither? Well, first of all, you need to know it's a critical point, right? So before you can even play this game, you need to establish that the point you're looking at is a critical point, right? If you don't have that, you have no business applying the second derivative test. Is there a second derivative test for 3 variables? No, there's not. Linear algebra is not kind to us there. 2 by 2 matrices are especially nice in terms of how the eigenvalues relate to this expression. In a 3 by 3 case, there's just no nice formula. So 3 by 3 case, I can really only reasonably ask you questions which are very much akin to problem 4, 5, or 6, where there is no second derivative test needed to determine the kind of local max or min. Simply analyzing the power series and thinking about sums of squares adding or taking away and adding, like this one, is just common sense applied to the critical point. There's no need for the second derivative test. The power series itself and a little common sense does it for you. All right, so one last comment about power series, then I'll move on here to the closed set test. Do you guys know what the formula is, generically speaking? Something like this. So if I have f of x1, x2, xn, and I want to write the multivariate power series, I could do something like this. It's the sum. I equals 0, well, let's say k equals 0 to infinity. All right, the sum of I1 ik equals 1 to n, with the understanding here, when k equals to 0, just write f of let's see here. I need another letter. I'll put bars on it. X bar 1, x bar n, right? And then here it is. We take the kth derivative of the function with respect to these variables. And then we multiply by x minus x, oh, excuse me, still wrong. X sub I1 minus x bar I1. X I2 minus x bar I2. X ik minus x bar ik. And this derivative is evaluated at the point x bar 1, x bar n. And that's the multivariate Taylor series for a function of n variables. Yep. Unfortunately, she got my attention before you, which is somewhat ironic. But you lost the opportunity because she beat you. I mean, I feel for you guys, but Stacy got it that time. She raised her, yeah, raising your hand. Like that's when, if you have to remind me though. Well, I thought you guys were going to actually ask me a question, like I was like, I'm telling you about all this interesting math, and I thought you're like, but sir, what if the function's blah blah blah? No, just points, points. Points are math too. Yeah.
Well, no, points are just arithmetic, not math.
Arithmetic, yeah, I think. But arithmetic seems like it's part of math. I don't know. Let's see here. We are what? 313. All right.